Okay, we're going to look at another indirect proof, P implies Q, using the contrapositive. So again, instead of assuming P and showing Q follows, we're going to use the logically equivalent implication that not Q implies not P. So as always with an indirect proof, we assume Q is false and we show that P is false. Looking over here at the example we're trying to prove, it should be pretty clear that we're not going to want to go from n squared plus 3 down to n. We're going to want to go from n up to n squared plus 3. In order to get from n squared down to n, we would have to take a square root, and there's only some integers who have integer square roots. So once you notice that the n is over here in the Q part of the implication, and the function of n, or statement about the function of n, is in the P for P implies Q, you should always understand that what we're really going to want to do is go backwards. Okay, now we're not going to show Q implies P. That's not an implication arrow there. What we're going to show is that not Q implies not P. Okay? So once we recognize this is the contrapositive, we can get to work on our proof. We're going to assume not Q. Now Q is over here, n is odd. Not Q would mean n is even. And I know I'm mixing up the colors a little bit here, but we're going to do the show over here that n squared plus 3 is even. Right? Not P would be that n squared plus 3 is odd. Okay? So now we're going to go from n is even to n squared plus 3 is odd, and that's going to be just as good as showing that if n squared plus 3 was in fact even up here, then n would be odd. So we start our proof. Again, once we rework our assumption and our objective to prove, we go about this like a direct proof. So n is even means n equals 2k, and now we're going to show that n squared plus 3 is odd. That means we want to show that n squared plus 3 equals 2 times sum L plus 1. So again, we start with n equals 2k. We move to create or construct n squared plus 3. That would be the quantity 2k squared plus 3, which algebraically 4k squared plus 3. And again, anytime we're trying to show something's odd, we need this plus 1 over here. So we're going to take the plus 1 out of the plus 3 and write that plus 3 really as 2 plus 1. So then we can factor a 2 out of the first part of it and get it into the format we want. 2 times a integer plus 1. As long as k is an integer, squaring, multiplying by 2, and plus 1 won't interrupt its integer status or won't affect its integer status. But trying to get from n squared down to n, taking the square root of something like 3 or 10 or 14 would cause a problem. Forget about negative numbers. Okay? So this shows us that n squared plus 3 is really 2l plus 1, and we can therefore conclude that n squared plus 3 is odd. Right? That's the end of our proof. And again, it may seem a little bit unsettling because we didn't prove directly what they were asking us to show, but again, this logical equivalence holds, so it's just as good as doing the original proof. Okay, so now it's time for you to practice some of these. After you do some indirect proof examples, make sure you put a couple direct and indirect side by side so you know when to use which approach. Again, the focus is really on the n. If n was part of the if statement, you could go from n to the function of n, you would use direct proof. But in these cases that we just did, the n was part of the Q or conclusion, we have to go in the opposite direction.